Hey guys, good evening and welcome back again to your Unacademy NEET English channel. I hope all of you are doing great, having a good time. So people, quickly let me know in the chats if all of you can hear me, if I'm perfectly audible and visible to every one of you. Let me know quickly in the chats, everyone, if all of you can hear me, if I'm perfectly audible and visible to every one of you. Good evening, everyone. Good evening and welcome back. Good evening, good evening. Good evening, guys. Good evening, people. So I believe I'm perfectly audible and visible to everyone, yeah? Am I? Perfect. So guys, today we are going to solve the questions from the chapter General Organic Chemistry, right? GOC. Well, the last chapter which we did, that was the thermodynamics. We did the thermodynamics question practice in the last session. And today we are going to cover one more question practice session of one more important chapter. And you know, the chapter is your General Organic Chemistry only. Yes? Yes, Ria, just do that. Just do that. So let me know once in the chats, have you guys studied your GOC once, at least? From anywhere. Does not matter. Let me know once in the chats if you guys have studied this particular chapter at least once. Say yes or no in the chats, everyone. Say yes or no in the chats, everyone. Let me know quickly in the chats if you have studied this particular chapter before. Quickly, people, I'm looking at your chats only. All right, that's great, that's great. Perfect. Then I believe if you have studied this chapter, then I believe you should be in a position to solve each and every question on your own. You should be in a position to solve each and every question, my dear students, that too on your own, right? And you know, your GOC, it is one of the scoring chapters of your chemistry, right? Because whenever a question is asked from the general organic chemistry part, it's most of the times the easy question, right? We call them as the easy kill questions when it comes to the NEET examination, basically. Okay? Chalo. Without wasting a lot of time, let's get going. Let's get started with the first question, which is on your screen. Which of the following possesses the sp carbon in its structure? In which of the structure, my dear students, do you see sp hybridized carbon? What do you think? I would want your answers in the chats. I would want your answers in the chats. I would want the chats to be continuously running in the today's session. Because I hope, and I'm pretty much sure, you will be solving each and every question on your own. In which of the following structure you can see the sp hybridized carbon? I want to see the answers in the chats. I want to see the answers in the chats, people. Absolutely. Absolutely. So my dear students, in the structure number 3, if you look at this particular carbon, how many sigma bonds it's forming? It's forming 1 and 2. It's forming 2 sigma. Perfect. So if it is forming 2 sigma, that means its hybridization has to be sp. So it's going to be option C, which is going to be the correct answer of this particular question, which was very simple and basic, right? A basic question this was, wherein you were supposed to check the sp hybridized carbon in all of these structures. Correct? All right. Look at this particular question, guys. The question asked in your NEET 2017. The correct statement regarding electrophile is. There are 4 statements which are given. I would want you guys to read all of these statements one by one and let me know what exactly the electrophile is. The correct statement regarding the electrophile, electron-loving species. Electron-loving species. electron loving species. If you look at the option 1 says that electrophile is a negatively charged species. Electrophile is a negative charged species. Is that right? No. Electrophile is a negatively charged species. No. Electrophiles are generally neutral species and can form a bond by accepting a pair of electrons from the nucleophile. Look at the next option. Electrophile can be either, this is the one. Electrophile can be either neutral or positively charged species and can form a bond by accepting a pair of electrons from the nucleophile. So option D is the one that is the correct definition of the electrophile, right? That is the correct statement regarding the electrophile. Electrophile can be neutral, it can be positively charged as well, right? Electrophile is, it can be neutral or it can be positively charged species and it can form a bond by accepting a pair of electrons from the nucleophile. Again, a very simple definition based question this is. Now, one more question which was asked in your NEET 2017. Look at this question. Which of the following is the electrophile? Which of the following is the electrophile? Dear students, this is something which everyone should solve. This is something which everyone should solve. Which of the following is electrophile among all? What do you think? I want everyone to let me know in the chats. Quick. Electrophile. Electrophile means electron-loving species. It can be neutral or can be positively charged. It can be neutral or positively charged. Right? A PDF of this session you will be getting in my Telegram channel, which is Wassim Bhat Chemistry Official. All right. My dear students, this is the electrophile over here. If you see your CCl2, correct? How many electrons it has right now, this carbon? It has got 2, 4, 6 electrons in its outermost shell. How many should be there? There should be 8 electrons. But how many are there? 6 electrons. Perfect. Right? So it behaves like the electrophile. The octet of this particular carbon is not complete. It behaves like the electrophile. Yes, dichlorocarbene. Dichlorocarbene. It's one of the famous electrophiles if you would have studied the organic chemistry. All right. Look at this particular question. These are some 4 different questions. 4 different questions. You are supposed to arrange the species as per their stability order. What do you think? You are supposed to arrange these species as per their stability order. My dear students, first of all, there's a positive charge on carbon, positive on nitrogen, positive on oxygen, positive on fluorine, right? If you look at all these elements, they belong to same period. And whenever we are supposed to check the stability of the charges on the elements which belong to same period, how do we do that? We do that with the help of electronegativity. You should know, if the elements belong to same period, then you are going to talk about the stability in terms of electronegativity. And remember 2 things. Negative charge is more stable on more electronegative element, and positive charge is more stable on less electronegative element. Right? So these are all positively charged species, and positively charged species, right? A positive charge will be stable on less electronegative element, right? So this is going to be the stability order. Correct? Look at the next one. Carbon carrying negative, nitrogen carrying negative, oxygen carrying negative, fluorine carrying negative. Again, these are the elements which belong to same period. And in the period, we talk in terms of electronegativity. And you know, negative charge is more stable on more electronegative element. So this is going to be the stability order of these charges over here. Correct? Similarly, my dear students, if you talk about sulfur carrying negative, chlorine carrying negative, sulfur and chlorine, they again belong to sulfur and chlorine. They belong to same period. And in the period, we again talk in terms of electronegativity. And you know, negative charge is more stable on more electronegative, right? So negative charge on chlorine will be more stable than that of negative charge on sulfur. Simple. Oxygen, sulfur, Se and Te. Oxygen, sulfur, Se and Te. Do these elements belong to same period or same group? These elements belong to same group. These elements belong to same group. And in the group, if you want to talk about the stability of the charges on the elements which belong to same group, you are not going to talk in terms of electronegativity now. You'll be talking in terms of volume charge density. You'll be talking in terms of volume charge density, which is nothing but, which is defined as the ratio of charge on the species divided by size of the species. And remember, stability, that is inversely proportional to the volume charge density. Stability is inversely proportional to the volume charge density. This is something, this is the rule which you are going to remember. Whenever you are supposed to compare the stability of the charges on the elements which belong to same group, you'll be talking in terms of VCD, volume charge density, right? Now tell me the answer of the question. Oxygen carrying negative, sulfur carrying negative, Se carrying negative, Te carrying negative. Down the group size increases. Down the group size increases. So over here, in case of T, the size is maximum. Maximum the size, more the size, lesser the VCD. Lesser the VCD, more is going to be the stability. So which one do you see maximum stable among all? It's going to be the last one, which is going to be the maximum stable among all. I believe I'm clear to everyone. So my dear students, here from this particular slide, you have to remember 2 points. Whenever you are supposed to compare the stability of the charges on the elements which belong to same period, you'll be talking in terms of electronegativity. And whenever, my dear students, you need to compare the stability of the charges on the elements which belong to same group, you'll be talking in terms of volume charge density, right? Perfect. Now, can you answer these questions? Can you answer these questions, guys? Well, you should be in a position. You should be in a position to answer these questions. Vishal, there is a lot of more questions added. Just wait. What do you think about this one? What is the correct answer of this particular question? Quick. Quick, people. Everybody. Again, it's simple. Nitrogen carrying negative, phosphorus, arsenic, antimony, right? Perfect. So, nitrogen, phosphorus, arsenic, antimony, they belong to same group. So, you'll be giving the answer as per your volume charge density. More the size, lesser the VCD, more the stability. So, this is the order, right? See, oxygen carrying negative, sulfur carrying negative. Oxygen and sulfur, they belong to same group. Again, VCD. More the size, lesser the VCD, more the stability. Right? Perfect. My dear students, look here. Single bonded carbon carrying positive, double bonded carbon carrying positive, triple bonded carbon carrying positive. Which of the following carbons has got more S character? You should be knowing this particular carbon among all the underlined carbons has got more S character. More the S character means more the electronegativity, right? And positive charge is more stable on less electronegative. If positive charge is more stable on less electronegative, then this is going to be the order. Correct? Look at the next one. Again, single bonded carbon, double bonded, triple bonded. This carbon has got more S character, more electronegativity, and negative charge is more stable on more electronegative. So this is going to be the order over here. I believe this is super clear to everyone. I'm moving on to one more. Just a second. All right. These are again the 3 questions which you can easily solve. I believe that. These are 3 more questions and I would want the answers in the charts. My dear students, negative, 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 right? It's a 3-membered ring, 4-membered, 5-membered, 6-membered, right? Which of the following ring has got more angle strain? Which of the following ring among all these 4 has got more angle strain? If you talk about the first ring, only 3 carbon atoms are here. So there is more angle strain. And more angle strain means more electronegativity. More angle strain means more electronegativity of the atoms. So this particular carbon here would be more electronegative than that of this one, then that of this one, then that of this one, right? And you know negative charge is more stable on more electronegative. So this is going to be the order over here. Perfect. Look at the next one. This carbon is more electronegative as compared to this particular carbon, right? And you know positive charge is more stable on less electronegative element. So this is going to be the stability order over here. Okay. What do you think about this one? Carbon carrying negative, nitrogen carrying negative. Carbon carrying negative, nitrogen carrying negative. And both these elements, they belong to same period. Both these elements belong to same period. Right? So you should be talking in terms of electronegativity. You know, negative charge is more stable on more electronegative element. Now you must be thinking nitrogen is more electronegative element here. But my dear students, if you look carefully, this is your sp hybridized carbon. This is your sp3 hybridized nitrogen. And remember, electronegativity of sp hybridized carbon is more than that of electronegativity of sp3 hybridized nitrogen. So which one is more electronegative here? this carbon here is more electronegative, and negative charge is more stable or more electronegative. Right? Perfectly clear? All right. Look at this particular question, guys. These are again two more questions. Arrange the following according to their stability order. Arrange the following as per their stability order. All of these are the carbocations, right? And carbocations, you should know, they are stabilized by electron donating groups. Carbocations are stabilized by electron donating groups. Well, if you look at CH3, it is electron donating. This is also electron donating. This is electron withdrawing. This is electron withdrawing. Electron donating groups, they stabilize the carbocation, right? And electron withdrawing group, they destabilize the carbocation. So which of the following carbocation is least stable? I would say C is least stable. C is least stable. Now, you have got CH3 and CD3. CH3 and CD3. This is present at the meta position. This is also present at the meta position. At the meta position, they are going to operate which effect? Inductive effect, right? This is going to show plus I. This is going to show plus I. Now, which one shows more plus I? CD3 or CH3? In the series of plus I, CD3 has got more plus I. More plus I means more stable, right? So B is maximum stable, followed by A, followed by C. Is this clear? Look at the next one, guys. Look at the next one. If you look here, these are again the carbocations. Nitro group attached. Here also the nitro group is attached. Perfect. Nitro is electron withdrawing group. Perfect. Nitro is electron withdrawing group. Now tell me, which one is going to be more stable? My dear students, first of all, electron withdrawing groups, they destabilize the carbocation. So I would say A would be maximum stable, because in A, there is no electron withdrawing group attached like nitro. But among B and C, electron withdrawing. Now here, electron withdrawing is closer to the positive charge. It is closer to the positive charge. If electron withdrawing is closer to the positive charge, that means this is going to be the least stable. C is going to be least stable, and this is going to be the order A, B, C. Am I clear with this? Am I clear with this? Yeah? All right. Let's move on to one more question, guys, then. Let's move on to one more question. What do you think about this one? These are again two questions, basically. These are again two questions. You have to arrange them as per their stability order. You can see you are again given with the carbocations, right? This is electron donating. Electron donating groups, they stabilize the carbocation. Here the electron donating group is closer towards the positive charge. So I would say C would be maximum stable, followed by B, followed by A. This is going to be the order. Correct? Look at the next question, guys. Look at the next question. Again, you have got carbocations over here, right? Look at this alkyl group. This alkyl groups are electron donating, right? This alkyl group is going to show plus I. Here also the alkyl group is going to show plus I. Here also the alkyl group is going to show plus I. Now, which alkyl group among these three will show more plus I? Which alkyl group among these three will show more plus I? Simple. More the branching at the free valent carbon. More the branching at the free valent carbon, more the plus I. And more the plus I means more is going to be the stability. So which one is going to be maximum stable? I would say B, followed by C, followed by A. This is going to be the order of the second question. I hope this is clear to everyone. I hope this is clear to everyone. I hope this is clear to everyone. Now, these are again two more questions which you should be in a position to solve. So let me know the answer in the chats quick. Let me know the answer in the chats quick. A, B, C. I'm waiting for your answers in the chats. I'm waiting for your answers in the chats. Why this X-star gamer is giving these angry looks? Yeah? Who you are giving these angry looks? Me? If yes, let me know in the chats. So people are saying ACB is the order. Is that? ACB? Let's have a look. So first of all these are your carbocations, right? This is your alkyl group attached at the meta position, so plus I. Nitro group at the meta position, so it's going to show minus I. CN at the meta position, minus I, right? So this is electron donating group. This is electron withdrawing. This is also withdrawing, right? And electron donating groups, they stabilize the carbocation. So A is going to be maximum stable. A is going to be maximum stable. Now, nitro is more withdrawing than CN. Nitro is more withdrawing. So B is going to be least stable and C I'll keep in the middle. So this is the order. This is the order. My dear students, among these two, this is the carbon carrying positive, this is the carbon carrying positive, right? So which is going to be more stable among these two? Quick. Which one is going to be more stable among these two? This is something which you can easily solve, guys. There is no need to think a lot. What is going to be the order? A or B? Which one is more stable? A or B? Which one is more stable? It's pretty much simple. B is going to be more stable than that of A. Because over here you can see there's a double bond. Double bond means more S character, more electronegativity. Right? Perfect. All right. Let's move on to one more. The question asked in your NEET 2013. The question asked in your NEET 2013. Arrange the following in the increasing order of their stability. These are again the carbocations which are given to us. We have to arrange them on the basis of their stability. Right? We have to arrange them on the basis of their stability. Quickly, guys. You can use your hyperconjugation. You can use your hyperconjugation concept. More the alpha hydrogens, more is going to be the stability of the carbocation, right? More the alpha hydrogens, more is going to be the stability of the carbocations. So if I ask you, where do you find maximum alpha hydrogens among the following options? Where do you find maximum alpha hydrogens among the following options? If you look at the second option, it is your C positive, CH3, 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 perfect. So 3, 6 and 9. These are the 9 alpha hydrogens which we have got here. So this particular carbocation is stabilized by how many alpha hydrogens? 9 alpha hydrogens, which is the maximum among all, right? Which is the maximum among all, right? If you look at this particular carbon, it is being stabilized by how many alpha hydrogens? 3 and 3, 6, 6 to 8. It is stabilized by 8 alpha hydrogens. Correct, guys? Similarly, you can check the rest. So, as far as I can see the options, it is going to be option B, which is going to be the correct answer among all, right? E is going to be the least stable one because there is no alpha hydrogen attached over here. Okay? Simple and basic question this was. All right. What do you think about this one? These are again 2 more questions which you have on your screen. And you should be able to solve these 2 as well. Look at these 2, guys. Well, look at them carefully. These are not your carbocations. These are now the carbanions. These are your carbanions, right? These are your carbanions. And you know, when you talk about your carbanions are stabilized. Your carbanions are stabilized by electron withdrawing groups. Your carbanions are stabilized by electron withdrawing groups. And I would say electron donating groups, they destabilize the carbanion. Electron withdrawing group stabilizes the carbanion and electron withdrawing group, it destabilizes the carbanion. Now tell me the answer. You should be able to solve this easily. See, guys, this is CD3, CH3 and CT3. Again, you can use the isotopic effect here, right? See, this is your electron donating group. It shows plus I at the meta position. It is also going to show plus I. This one is also going to show plus I, right? But when you look at your plus I series, CT3, this shows more plus I. This shows more plus I, followed by this one, right? So which one comparatively among these 3, which one is less, which one is comparatively less donating? Which one is comparatively less donating? It is going to be B, right? I told you already, carbanions are stabilized by electron withdrawing. they are destabilized by electron donating. These are all electron donating groups, but this one is more donating. More donating means C is going to be least stable, followed by your A, followed by your B. B is going to be the most stable among all. Correct? If you look at the second question, guys. See, this is the carbon carrying negative. Even this is the carbon carrying negative. This is the carbon carrying negative. Withdrawing, right? Nitro is withdrawing, F is also withdrawing. Now, electron withdrawing groups, they stabilize the carbanion. So, which one will be most stable among all? Which one would be most stable among all? See, A would be least stable. That is for sure. Now, among B and C, this is also withdrawing, this is also withdrawing. Which one is more withdrawing? You should know it, guys. You should know it. Give me the answers in the chats. Give me the answers in the chats, guys. Give me the answers in the chats. Give me the answers in the chats. The order is going to be B, C, and A. Nitro is more withdrawing than F, right? More the withdrawing group attached, more is going to be the stability of carbanion. All right. This is again one more question. What is the order of the stability among these two? This is something which you should be able to solve easily now. What do you think? What do you think? See, guys, sulfur carrying negative, oxygen carrying negative. Sulfur and oxygen, they belong to the same group. And in the group, you talk in terms of volume charge density. More the size, lesser the VCD, more the stability. So this is the stability order. Right? This is the stability order. Perfect. This is your sp hybridized carbon. This is your sp3 hybridized nitrogen. Which one has got more electronegativity? I told you already. sp hybridized carbon has got more electronegativity than that of sp3 hybridized nitrogen. And you know negative charge is more stable than? Negative charge is more stable and more electronegative. So this is going to be the order here. Yeah? I hope you are getting all these things properly. All right. Give me the order of these two questions as well. These are the carbanions. You have to arrange them as per their stability. CH3 group, it is electron donating plus I. CN shows minus I here. Nitro also shows minus I here. And you know, your carbanions, they are stabilized by electron withdrawing groups. So which one is more withdrawing among these two? C is more withdrawing. Nitro is more withdrawing. So C is maximum stable, followed by B, followed by A. Right? Now, this is NF3 positive here. NF3 positive. This is F and this is CD3. Right? NF3 positive at the meta position is going to show minus I. Chlorine at meta is going to show minus I2. And this CD3, right, it's going to show plus I. And you know, this is withdrawing, this is withdrawing, this is donating. Electron donating groups, they destabilize the carbanion. So C is going to be the least stable. Now, among A and B, A is going to be more stable, followed by B. Right? This is the order. This is the order, guys. Perfect. I hope this is all clear. All right. These are two more questions which you have on the screen, and I would definitely want you guys to give them a try. Quick. What do you think? Arrange the following according to their stability order. Again, the similar sort of question. Guys, oxygen, you know, it's withdrawing, right? It's withdrawing. Here, there is no oxygen attached. Oxygen attached. Oxygen attached. In the structure B, oxygen is comparatively closer. In the structure B, oxygen is comparatively closer. So B is going to be maximum stable, followed by A, and at the end, followed by C. Correct? Now, sulfur carrying negative, oxygen carrying negative. Okay? Sulfur carrying negative, oxygen carrying negative. Sulfur, oxygen, they belong to same group. In the group, VCD plays a role. right? So this has got more size. Sulfur has got more size, less VCD, more stability, right? So among A and B, which one is more stable? A is more stable than B. Now among B and C, have a look. Oxygen carrying negative, nitrogen carrying negative. Oxygen, nitrogen, they belong to same period. In the period, electronegativity plays a role. And you know, negative charge is more stable and more electronegative. Oxygen is more electronegative, so B is going to be more stable than C, right? Similarly, among C and D, nitrogen carrying negative, carbon carrying negative. They belong to same period. Again, electronegativity plays a role. So C is going to be more stable than D. So what is the order? Order is going to be A followed by B followed by C followed by D, right? That's going to be the order of stability here. A, B, C, D. Again, a common, simple question this was, and I believe you would have solved it easily. Okay, these are two more questions, which are based on the stability order. What do you think? What do you think? Among A and B, which one is more stable? See, this is the carbanion basically, negative charge. Here also you have got the negative charge. Chlorine is attached, more withdrawing. Electron withdrawing groups, they stabilize the carbanion. So A will be more stable than B. F negative, I negative. Which one is more stable? See, fluorine and iodine, they belong to same group. In the group, VCD plays a role. More the size, lesser the VCD, more the stability. So this is the stability order here. Yeah? I hope you are remembering all this stuff, people. I hope you are remembering all this stuff. NEET 2018. This, I believe, everyone can solve with a closed eyes. What do you think? These are carbanions. These are not carbocations, right? This is negative, negative, negative. Single bonded carbon, double bonded carbon, triple bonded carbon. Which one has got more S character? This particular carbon will be having more S character than this, than this. More the S character means more the electronegativity. And you know, negative charge is more stable on, more electronegative, right? So this is going to be the order. 3 is going to be maximum stable, followed by 2, followed by 1. So it's option B. Yes? Perfectly done. Let's move on to one more. NEET 2018. NEET 2018 question. Which of the following is correct with respect to minus I? Which one shows more minus I? See guys, look at the first atom. Nitrogen, oxygen, fluorine. Nitrogen, oxygen, fluorine. Which one is more electronegative? Fluorine is more electronegative. So fluorine will be more withdrawing. So fluorine shows more minus I than that of this OR, than that of this NH2, right? So which one is going to show more minus I? It's going to be F followed by this, followed by this. Option B is the one that's going to be the correct one, right? You are supposed to arrange them as per their what? Minus I power. Minus I means withdrawing power. More electronegative will be more withdrawing here in these cases. Perfect. All right. Which arrange the following according to their stability order. These are the resonating structures which are given to me. These are the resonating structures that are given to me, and you're supposed to arrange them as per their stability order. Quick. Quick, people. What do you think? Quickly, guys, give me the answer of this question. Quick. You should be able to solve this. See, my dear students, first of all, whenever you are supposed to arrange the resonating structures as per their stability, what is the first thing you always do? You always count the covalent bonds first. See, if I count the bonds here, 1, 2, 3, 4, 5, 6. So you can see there are 6 these underlined bonds which are shown over here. 1, 2, 3, 4, 5, 6. Again 6 here. Look here, 1, 2, 3, 4, 5, 6. Again 6 here. So the bonds in every structure is same. If the bonds were different, then more the bonds means more the stability. But over here, bonds are same. Bonds are same, so you cannot talk in terms of bonds here. You cannot not talk in terms of covalent bonds. Number 1. If the bonds were different, then you could have arranged them. But bonds are same, so you cannot arrange them as per their stability. Now, what is the next thing? Next thing is, which of the resonating structure is there which has got no charge on the atoms? Look at the first structure. In the first structure, there's no charge on any atom, right? So A is going to be maximum stable. A is going to be maximum stable because its atoms does not contain any charge. Perfect. Now, among these two, what do you think now? Among these two, what do you think? See guys, oxygen here is carrying negative. Here also oxygen is carrying negative. So do not decide as per oxygen. Nitrogen carrying negative, positive. Oxygen carrying positive. Oxygen carrying positive, nitrogen carrying positive. Positive charge is more stable on less electronegative. So nitrogen is less electronegative than this oxygen. So C would be more stable than that of B. So this is going to be the stability order of these three structures which were given to me. Am I clear with this? Well, I can see all the students have already given the answer ACB. That's perfect. All right. Now arrange these three resonating structures as per their stability. And I would want you guys to follow the same thing what I told you till now. First, calculate the bonds. Calculate the bonds. This is 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 covalent bonds which I have mentioned over here. 1, 2, 3, 4, 5, 6, 7. The underlined ones are only 7. 1, 2, 3, 4, 5, 6, 7, 8. So 8 bonds here. More the bonds, more the stability. Lesser the bonds, lesser the stability. So here you have got 7 bonds which I've underlined. So B is least stable. B is least stable. Now, among A and C, if you look at A, atoms do not carry any charge, right? If you look at C, here atoms carry certain charges. That resonating structure wherein atoms do not carry any charge, that's considered to be more stable. So A is more stable, then comes your C, then comes your B. So this is the order over here. I hope this is clear to everybody. All right. Now, what about these two questions? Again, arrange the resonating structures as per their stability. See guys, first thing which I told you already, count the bonds, right? 1, 2, 3, 4. 1, 2, 3, 4. Bonds are same. Now, the first one, its atoms do not carry any charge. So more stable. So A would be more stable than B. Now, among A, B, C, first of all, count the bonds. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Over here in this particular case, 1, 2, 3, 4, 5, 6, 7, 8, and here also 9. So 9 bonds. Here in this particular case, how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 bonds. Perfect. Right? So now give the order. You're done. You're sorted. Lesser the bonds, lesser the stability. So B is the least stable one. B is the least stable one. Among A and C, here atoms do not carry any charge. Here atoms carry charge. So A is going to be more stable than C, followed by B. So ACB is going to be the order. Right? ACB is going to be the order. Correct, guys? I hope I'm clear with this. Did I count the bonds correctly here? 2, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9. Wait, I think I counted the bonds incorrectly here in this case. Just a second. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This also contains 10 bonds. This also contains 10 bonds. Now wait. This also contains 10 bonds. So everywhere there are 10 bonds basically. Now, if bonds are same, now see, first one, its atoms do not carry any charge, so A is going to be maximum stable. Now, among B and C, oxygen carrying positive, carbon carrying negative. Oxygen carrying positive, carbon carrying negative. Now, talk in terms of charge separation, right? Unlike charges, here also you have got unlike charges. More the distance between unlike charges, lesser the stability. More the distance between unlike charges, lesser the stability. So, the order is going to be A, B, C only. Yeah, it's correct. Done? Let's move on. These are 2 more questions based on the stability of the resonating structures, and I believe you can easily solve them too. Give it a try, guys. Give it a try. Give it a try. Count the bonds first of all. 2, 4. 1, 2, 3, 4. 1, 2, 3. So lesser the bonds, lesser the stability. So 3 is least stable. 3 is least stable. Now among 1 and 2, if you look carefully, nitrogen carrying positive, perfect. So you cannot decide on the basis of this nitrogen. This nitrogen carrying negative, carbon carrying negative. Nitrogen negative, carbon carrying negative. Negative charge is more stable and more electronegative. So A is going to be more stable than B. A is going to be more stable than B. Right? So 1, 2, 3 is going to be the order here. Matlab ABC is going to be the order. Look at the next one. Again, follow the similar procedure first. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Right? So 6 bonds. What does it tell me? It tells me that C and D is going to be more stable than A and B. C and D is going to be more stable than A and B. Right? Now, among C and D, which one would be more stable? Among C and D, which one would be more stable? C, carbon carrying negative, carbon carrying negative. Nitrogen carrying positive, nitrogen carrying positive. Now talk in terms of charge separation here. More the charge separation, lesser the stability. So C is least stable, D would be more stable comparatively, right? Just a second. D would be more stable, right? D would be more stable. Then comes your C. Now among A and B, bonds are same. Now see, carbon carrying positive, here carbon is carrying positive. Perfect. Carbon carrying negative, perfect. Carbon carrying positive, carbon carrying negative, carbon carrying positive, carbon carrying negative. But if you see, this is lone pair negative. Repulsions means less stable. So B would be more stable, followed by A. B would be more stable, followed by what? Followed by A. So this is going to be the order of the resonating structure stability over here. Correct? Correct, people? Is it clear? Is it clear to everyone? Yeah? All right. Tell me the answer of this question. Among these two, which one is more stable? Among these two, which one is more stable? Quickly. Which one is more stable among these two? It's pretty much simple, guys. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. More bonds, more stability. So B is more stable than that of A. Nothing to do, right? What do you think about this one? What do you think about this one? Which of the following molecule is the least resonance stabilized? Least resonance stabilized. What do you think? This is again one simple question and you should be able to solve this question too. Quick, guys. Be quick. See, first of all, 2, 4, 6. 6 pi electrons involved in the cyclic conjugation. Again, 2, 4, 6. 6 pi electrons, right? 2, 4, 6. 6 pi electrons. Cyclic also. Planar also. 6 pi electrons also. Cyclic, planar 6 pi. Cyclic, planar 6 pi. Look at this particular carbon here. It is sp3 hybridized. See, this particular species is aromatic. This particular species is aromatic. This particular species is aromatic. This one is non-aromatic. And you know non-aromatic ones, they are less stable than the aromatic ones. Right? So it's going to be option 4. Done and dusted. What do you think about this one? Order of stability of the following resonating structures. What is the stability order? Again, you are going to follow the same concept. Count the bonds first of all. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Bonds are same. So you cannot decide on the basis of bonds. Now, is there any structure wherein the atoms do not carry the charge? Yes, structure number 1. So 1 is more stable. Now, among 2 and 3. Nitrogen positive, carbon negative. More the charge separation between unlike charges, lesser the stability, right? So second is going to be more stable than that of third. So 1, 2, 3 is going to be the order here. Perfect. 1, 2, 3 is going to be the order here. All right. One more question. Compare the bond lengths this NC bond length, NC bond length, NC bond length, NC bond length. You have to compare these bond lengths, guys. You need to compare these bond lengths, right? If you look at this particular bond, it's a pure single bond. This one is a pure double bond. Pure single bond, pure double bond, right? Bond length of pure single bond is considered to be maximum and pure double bond length would be minimum. Perfect. Now, among 3 and 4, if you look at this particular nitrogen, it has got the lone pair. Even this nitrogen has got the lone pair, right? So pi sigma lone pair, pi sigma lone pair. Resonance. Due to resonance, this particular bond is getting the double bond character. Due to resonance, this particular bond is also getting the double bond character. Now, where is the resonance more? In third or fourth? In fourth, resonance is more. Pi sigma lone pair. In fourth, resonance is more. More the resonance, more the double bond character. More the double bond character here, lesser the bond length. Lesser the bond length. So fourth will have lesser bond length than that of third. Right? Clear, guys? Is it clear? Is it clear? Say yes or no in the chats quick. Say yes or no in the chats quick. Perfect. All right. Arrange the following according to their stability order. You have to arrange them as per the stability order. Look here, guys. One thing which I believe all of you would be knowing, negative charge holding capacity, negative charge carrying capacity of oxygen is greater than that of negative charge carrying capacity of 10 carbon atoms. Do you know that? Negative charge carrying capacity of oxygen is even greater than the negative charge carrying capacity of 10 carbon atoms. Now you have to arrange these as per the stability, right? Say, this negative can come here, this pi bond can get shifted here, so negative will be here also, right? So negative is coming on this oxygen as well as this oxygen. Here, due to resonance, this will come here, this will go here, and it carries negative. Then this negative comes at this spot. This pi bond breaks in this direction, so negative. Then it comes here, and this breaks in this spot. This gets negative. So this carbon is getting negative, this is getting negative, this is getting negative, and this is getting negative. Over here, oxygen is already carrying negative. Now it can come here. The negative can shift here. Now this negative can go here, right? Negative can come here. Now this is the process which can happen due to resonance. Perfect. Due to resonance, negative charge is coming on 2 oxygen atoms. Perfect. In all the 3 cases, there is only one case wherein negative charge is coming on 2 oxygen atoms. And negative charge carrying capacity of oxygen is very, very, very high. So I would say A would be maximum stable. Now among B and C, in case of C, negative charge is coming on oxygen. Here negative charge is not on the oxygen. So I would say C would be more stable than that of B. So this is going to be the order here. That is A, C, B. I hope this is also clear to everyone. Correct? Let me move on, guys. Among these two, which one is more stable? Among these two, which one is more stable? See, you have got the positive charge on this carbon. Now this pi bond can shift here. The positive charge can come here, right? Over here, this pi bond can shift here, and this carbon gets positive. This pi bond can shift here. This carbon gets positive. This pi bond can shift here. This carbon gets positive. Perfect. So in short, if you look carefully, among these two, where are the resonating structures more? Simple. Where are the resonating structures more? In case of B, if B has got more resonating structures, that means more resonance. More resonance means more stability. So B is going to be definitely more stable than that of A. Okay, arrange these molecules. Arrange these as per their stability. If you look at all of them carefully, let me show you one by one. This negative can come here, this pi bond can shift here, and negative can finally reach to this carbon. Similarly, this can come here, and this pi can shift here, so negative can come on oxygen as well, right? This can come here, this pi bond can shift here, so negative can come on this particular nitrogen. Shift, and shift this pi bond as well. Perfect. Now shift this pi bond will be here in the form of negative. Perfect. Now this negative comes here. This pi bond shifts here. This is negative. Now this negative comes here. This pi bond shifts here. This is negative. Perfect. These are all the following possible cases which I'm showing you. This negative can come here. This pi bond breaks in this direction. Negative here. Pi bond breaks here. Negative in this direction. Pi bond breaks here. Perfect. So what can you conclude from all of these? What can you conclude from all of these, people? What can you conclude from all of these? See, do you see any of the molecule where negative charge is coming on 2 oxygen atoms? Yes. In D, negative charge is coming on 2 oxygen atoms. Right? So D is going to be maximum stable. D is going to be maximum stable. So leave D aside. Leave D aside. So 2 oxygen atoms carrying negative, leave that. That's maximum stable. Now, which other molecules are there wherein 1 oxygen is carrying negative? Here 1 oxygen is carrying negative. Here also 1 oxygen is carrying negative. Oxygen carrying negative, oxygen carrying negative. No doubt oxygen is carrying negative here also, here also. But in this particular case, resonating structures would be more. So E would be more stable than that of B. E would be more stable than that of B, right? Now what all are left? What all are left? There is no electronegative element here, right? There is no electronegative element here. There is electronegative element nitrogen. Negative charge will be more stable on nitrogen, so C would be more stable. Now among A and F, negative charge is only coming on carbon, and also negative charge is coming on carbon, right? So among A and F, talk in terms of resonating structures. In case of F, resonating structures will be more, so more stability, and A would have lesser resonating structures. So this is going to be the final stability order of these molecules. I hope this is also clear to everyone. Yeah? I hope this is clear to everyone. All right. If this is clear, then tell me the answer of this particular question. Again, these are the carbocations which are given to us. Again, these are carbocations which are given to us. And we need to arrange these carbocations as per their stability. Now, what do you think? OH at the para position is going to operate plus M from here, right? OH at the meta position is going to operate minus I from here. Nitro at the para position is going to operate minus M from here, right? NO2 at meta is going to operate minus I. And SH at para is going to operate plus N, right? And when it comes to the stability of carbocations, carbocations are stabilized by electron donating groups. Carbocations are stabilized by electron donating groups. And you'll be prioritizing plus M showing group more, followed by plus H, followed by plus I, followed by minus I, followed by minus H, followed by minus M. This is going to be the order in which you are going to, give the answer. Perfect. So stability of carbocation. Is there anyone showing plus M? Yes, this is showing plus M, as well as this is showing plus M. And plus M showing group, they are going to stabilize the carbocation the maximum. Now, which one shows more plus M? Over here, there will be 2p2p overlap. Here, there will be 2p3p overlap. And 2p2p overlap is effective. So I would say, here the extent of overlap will be more. Perfect. So in short, I would say OH shows more plus M than that of SH. So 1 is maximum stable, followed by 5. Now 2, 3, and 4. 2, 3, and 4. You are going to prioritize minus I showing group first. Now OH and NO2. Which one is lesser? Minus I showing? NO2 shows more minus I than that of OH. So I'll be prioritizing OH first. And then I'll be prioritizing NO2, and at the end I'll be prioritizing minus M showing group. So this is going to be the stability order in this particular case, right? 1, 5, 2, 4, 3. 1, 5, 2, 4, 3 is going to be the order of this particular equation. Right, people? Simple, you just have to remember this, and you can solve each and every question based on this. I am moving on. Arrange the following as per their acidic strengths. Arrange the following as per their acidic strengths. My dear students, if you have got the acid HA, after losing H positive, it gets converted into A negative. This HA, after losing H positive, gets converted into A negative. If this was the acid, then this is something which I call as conjugate base. And you know, strength of acid is directly proportional to what? Stability of the conjugate base. strength of acid is directly proportional to the stability of conjugate base. More stable the conjugate base, stronger is going to be the acid. More stable the conjugate base, stronger is going to be the acid. Now, look at all the possible cases. So first of all, among these two, if you take H positive out, it becomes RO negative. If you take H positive out, it becomes RS negative. Perfect. So which conjugate base is more stable? Oxygen carrying negative, sulfur carrying negative. Same group, that means VCD. Size is more, VCD is less, right? So this conjugate base is more stable. More stable the conjugate base, stronger the acid. So RSH is going to be more stronger acid than that of ROH. Simple. Take H positive out, there will be negative charge on carbon. Take H positive out, negative charge on nitrogen. H positive out, negative charge on oxygen. H positive out, negative charge on fluorine, right? Now, which conjugate base will be more stable? Carbon carrying negative, nitrogen carrying negative, oxygen carrying negative, fluorine carrying negative. Negative charge is more stable on more electronegative. Negative charge is more stable on more electronegative. So I would say negative charge will be stable on fluorine. So the conjugate base which we get from HF, that is more stable. So what is going to be the acidic strength order here? This is going to be the acidic strength order. Perfect. Take H positive here out, oxygen carrying negative. H positive out, sulfur carrying negative. Oxygen, sulfur, same group, VCD. More size, less VCD, more stability. So conjugate base which we get here, that will be more stable. If conjugate base here is more stable, that means acidic strength would be more. Right? If you look at the next case, take H positive out, carbon carrying negative. Take H positive out, negative. Take H positive out, negative. This is triple bonded carbon, more S character. More S character means more electronegative. Negative charge is more electronegative on more, negative charge is more stable on more electronegative. Right? So the conjugate base which we get here, that will be more stable. More stable the conjugate base, stronger is going to be the acid. More stronger the conjugate base, stronger is going to be the acid, right? Now, here also, if you talk about it, if you take H positive out, carbon carrying negative. If you take H positive out, nitrogen would be carrying negative. This is sp hybridized carbon. This is sp3 hybridized nitrogen. And electronegativity of sp hybridized carbon is more. So conjugate base which we get here in the first case, that will be stable. That will be more stable. More stable the conjugate base in the first case, stronger is going to be the acid. So 1 would be greater than 2. I hope this is like super clear to everyone. Yeah? Am I, guys? Am I clear to everyone? All right. These are 2 more questions and you can easily answer them. You can easily answer them. What do you think now? What do you think? This is COOH. This is also your COOH, carboxylic. This is COOH. Here, electron withdrawing group is attached. Electron withdrawing groups, they increase acidic strength, right? This is withdrawing. This one here is donating. Perfect. Withdrawing groups, they increase acidic strength. So A would be maximum acidic, followed by what? Followed by B, followed by C. In the next case, if you think carefully, this is your carboxylic acid. This is your carboxylic acid. This is also your carboxylic acid. This is your phenol, this is also phenol. And carboxylic acids are stronger acids than that of phenols. Carboxylic acids are stronger acids than that of your phenols. Correct? So A and B will be more acidic than C and D. A and B will be more acidic than C and D. Because carboxylic acids, they are stronger acids than phenols. Right? Now, among A and B, which one will be more acidic? C. Nitro at meta position, CH3 at the meta position. So both, this is going to operate minus I, this is going to operate plus I. So this becomes withdrawing, and electron withdrawing group, they increase the acidic strength. So A would be maximum acidic, followed by B. Now, among C and D, this is withdrawing. Withdrawing means more acidic. So C would be more acidic than that of D. This is going to be the acidic strength order in this particular case. Yes, even JEE students can also watch it. Yes. There is no need to spam. You can watch it. Perfect. These are 2 more questions, guys. You have to arrange them as per their acidic strength. Can you do that? Arrange them as per their acidic strengths. Arrange them as per their acidic strengths. So COH, COH, COH. Reference everywhere is same. CN at the meta position minus I. CH3 at meta is going to show plus I. And F at meta is going to show minus I. Now, I believe you can easily solve this one. Same goes for the next one. But be careful here. Be careful in the next one. This is your carboxylic. This is phenol. This is carboxylic. Carboxylic acids are stronger acids than that of phenols. So phenol is going to be the least acidic among all, right? Now, among A and B, among A and B. A and B are carboxylic acids, but here there is electron withdrawing. So C would be maximum acidic, followed by A, followed by B. Correct, guys? All of this can be easily done. All of this can be easily done if you know the concepts. Now, if you look at these two questions, can you give the order of their acidic strengths? Can you arrange them as per their acidic strength order? First of all, check the reference. Reference is same everywhere. Reference is same everywhere. 3 fluorine atoms attached. Only 2 fluorine atoms attached. Just 1 fluorine attached. Fluorine is withdrawing, right? So more withdrawing means more acidic. So C followed by B followed by A. This is NF3 positive. Okay, here is the catch. See guys, this is your phenol. This is also your phenol. But this is your carboxylic acid. So C is going to be maximum acidic first of all. C is going to be maximum acidic. Carboxylic acids are maximum acidic. Now, among B and A, this is more withdrawing. NF3 positive. If NF3 is positive, is more withdrawing. So A would be more acidic than that of B. So this is the acidic strength order. CAB. Right? Perfect, guys. I hope this is clear. I hope this is clear. Again, guys, you have got 2 more questions. What do you think about this one? What do you think? This is the site from where hydrogen is going to leave as H positive. This is the site from where hydrogen is going to leave as H positive. Now, fluorine attached at the second carbon. Here, the fluorine is attached to the third carbon, right? So, withdrawing group is attached closer. Withdrawing group is attached far. Correct? So, this can be one of the logics. Or you can say, there are 3 fluorine atoms attached here. There are only 2 fluorine atoms attached. But this one is more appropriate reason. Fluorine is closer here. So, it will be more withdrawing here. I would say A is going to be more acidic than that of B. Now, if you take H positive out, you will be getting the conjugate base. If you take H positive out, you will be getting the conjugate base. H positive out, conjugate base. H positive out, conjugate base. Where would be the conjugate base more stable? See, this 3-membered ring is more electronegative, followed by this, followed by this, followed by this, right? If this is more electronegative, that means negative charge will be more stable here. So the conjugate base which is getting formed in the first case, that is more stable. If conjugate base formed in the first case is more stable, that means its corresponding acid has to be stronger. The order of acidic strength has to be this. Right? Right, people? I hope this is clear. Now, these are 2 more questions. CHF3 and CHCl3, which one is more acidic? CHF3 and CHCl3. If you take H positive out, it becomes CF3 negative. Perfect. If you take H positive out, it becomes CCl3 negative. Perfect. These are the conjugate bases. Now, which conjugate base is more stable? My dear students, this is a special case. Over here, chlorine. You have got fluorine here. Chlorine has got vacant d orbitals. Fluorine does not have any vacant orbital here. Fluorine does not have any vacant orbital. If chlorine has vacant d orbitals, so there is a possibility of back bonding. And back bonding stabilizes the conjugate base. So this conjugate base which we get here, that is more stable. More stable the conjugate base, stronger the acid. So this is the acidic strength order. Similarly, if you take H positive out here, you will get negative here. Take H positive out, negative here. Oxygen has it does not have any vacant orbital. Sulfur has got vacant d orbital. So there is a possibility of back bonding here. Back bonding stabilizes the conjugate base. And if back bonding stabilizes the conjugate base, I would say its corresponding acid has to be stronger. Right? So these sort of things, my dear students, can be easily solved if you know the approach. Okay. Arrange the compounds in the order of their acidic strength. So first of all, check the reference. Reference everywhere is same. From where hydrogen is going to leave as H positive. Right? Now Cl. Cl is here. CH3, NO2, OCH3. Now which one is going to be maximum acidic? Which one is going to be maximum acidic, guys? Maximum acidic. Quick. What is the answer of this question? This is something which you should be able to solve on your own, by the way. Quick. OCH3 at the para position shows plus M. Nitro at the para position shows minus M. Right? This shows your hyperconjugation. You're done. Right? Done with this. Done with this, right? I'm only representing the dominating effects of these groups. And you know, strength of acid is directly proportional to what? Electron withdrawing. And in electron withdrawing, minus M is maximum. Minus M followed by minus H followed by minus I. So third is going to be maximum acidic. Minus M followed by minus I followed by plus H followed by plus M. Is there any option like this? 3, 1, 2, 4. So it's going to be option C. That is going to be the correct answer of this particular question. I believe this is clear. I believe this is clear. What do you think about this particular question? Give it a try. I would want the answers in the chats. I would want answers in the chats. Everybody. Anyone done? People are saying option 2. Let me check it out. Okay, in all of these, if you look carefully, this is your phenol, this is also OH, this is your carboxylic, and this is also carboxylic. And you know, carboxylic acids are stronger acids than phenols, right? So 3 and 4 is definitely going to be more acidic than 1 and 2. Now, among 3 and 4, which one is more acidic? This is plus H, right? This is not showing anyone. So 3 is going to be maximum acidic, followed by 4th. Now, among these two, which one is going to be more acidic? Here is the withdrawing group, and in the first one, there is no withdrawing group. So 3, 4, 2, 1 is going to be the order. 3, 4, 2, 1. That means option A. Were you all writing option A only? Perfect. Perfect, guys. So first of all, be careful with the references. This is the point, huh? Your carboxylic acids, they are stronger acids than that of phenols. Do not directly jump into the effects shown by the groups. First of all, check the references. First of all, check the references. Now, this is something which I believe all of you can easily solve. What do you think? Which of the following acids have lowest pKa? Lowest pKa means maximum acidic strength. Lowest pKa means more Ka. More Ka means more acidic strength. So which one is more acidic? Which one is more acidic? First of all, the site everywhere is common, from where hydrogen is going to leave as H positive. This is the site. Now, if you see 2 chlorine atoms, 3 chlorine atoms, right? Perfect. 1 chlorine, 1 chlorine. More the withdrawing groups attached, more stronger the acid. So C is going to be stronger acid. C is going to be the stronger acid because there are 3 chlorine atoms attached. Which one of the following compounds is most acidic? Which one of the following compounds is most acidic? Wherein hydrogen can leave as H positive easily. Which of the following is more acidic? What do you think? This is an easy question, guys. Again, there is no need to think a lot about this. It's an easy question. It is an easy question. Absolutely, it's going to be option 2. Majority of the students are right. Why is that? Because if you talk about the lone pairs of this particular oxygen, they are in conjugation. When hydrogen leaves as H positive, the conjugate base which you get, that is resonance stabilized. Perfect. It's resonance stabilized, which is not the case in all the other molecules. So here the conjugate base is going to be more stable. And more stable the conjugate base, stronger the acid. You know it. In all the other cases, that's not. That's not the case in all the other options. Here, oxygen is not in conjugation. The lone pair of oxygen is not in conjugation. Here also it's not in conjugation. Here also it's not in conjugation. Right? A simple basic question this is. Okay. Arrange the following as per their basic strength. So these are basically three questions. These are basically three questions. You have to arrange them as per their basic strength. See guys, here the lone pair of nitrogen is localized. Here also it is localized only. Okay? Here also it's localized only. But what is the logic here? What is the logic? What is the logic, guys? Quick. One or two. Which one is going to be more basic? One or two. Which one is going to be more basic? I would say S character of this nitrogen is more. More S character, more electronegativity. So this lone pair of nitrogen will be held by electron strongly as compared to this lone pair. Perfect. So where is the lone pair more available? In the first case. Wherever lone pair is more available or the donation, stronger is going to be the base. Right? Talk about these two. Chlorine, fluorine. Fluorine is more withdrawing. Fluorine is more withdrawing. Perfect. If fluorine is more withdrawing, where can H positive attack easily? H positive can attack easily in the first case. Wherever species H positive is going to attack easily, I would say stronger is going to be the base. Now here also, which nitrogen has got lesser S character? This particular nitrogen has got lesser S character. Lesser S character means lesser electronegativity. So that means this lone pair is comparatively available as that of the other lone pairs. More the availability of the lone pair, more easily H positive can attack. So where can H positive attack easily? Here, right? So third is going to be maximum basic. Perfect. I hope this is super clear to everyone. All right, this is one more question. And I would want answers from you. I would want answers from you. Arrange the following according to their basic strength. Basic strength, right? First of all, reference everywhere is same. Reference everywhere is same. Now, OH at the para position shows plus M. SH shows plus M. O negative shows plus M. CH3 at the meta position shows only plus I. Right? And if you know, if we talk about the strength of base, it is directly proportional to electron donating groups, and plus M is maximum, followed by your plus H, followed by your plus I, followed by minus I, followed by minus H, followed by minus M. This is going to be the order which you are going to remember in order to give the order of the basic strength. Right? So now this is plus M, this is plus M, this is plus M. Anionic groups, they are more plus M showing. Anionic groups, they are more plus M showing. So 3 is more basic. Now among 1 and 2, which one shows more plus M? OH shows more plus M than SH. So I'll prioritize 1, then 2, and at the end I'll prioritize 4. So this is going to be the basic strength order. 3, 1, 2, 4. 3, 1, 2, 4 is going to be the basic strength order. All right. Look at this one. Look at this one, guys. Arrange the following in correct decreasing order of pKb. Decreasing order of pKb. See, lesser the pKb means more is the basic strength. Means more is the basic strength. So which one is maximum basic among all? Check that first. Which one is maximum basic among all? Quick. Which one is maximum basic among all? Quickly, guys. See, this lone pair on nitrogen is in conjugation with the ring. This lone pair of nitrogen is in conjugation. This lone pair of nitrogen is in conjugation. This lone pair of nitrogen is not in conjugation. It's a localized lone pair here, right? So this particular species is going to be maximum basic. So second is going to be maximum basic. So if second is maximum basic, it will have least pKb. It will have least pKb. So second should have least pKb. So option D is to be the one which is correct. Second should have least pKb. Correct, people? All right. You have to check among all these which one is aromatic, which one is anti-aromatic, and which one is non-aromatic. See, guys, First of all, it's cyclic, number one. sp2, 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 everywhere it's sp2, so it's a planar one. Cyclic as well as planar. And 2, 4, 6. There are 6 pi electrons involved in the complete cyclic conjugation. So this is supposed to be aromatic. It's aromatic one. It's following Huckel's rule, right? Look at this one. Molecule is cyclic, molecule is planar also, right? Every carbon is sp2 hybridized. That's something which is understood. Now, how many pi electrons? 2, 4, 6, 8, 10, 12, 14. 14 pi electrons means it is following the Huckel's rule, 4n plus 2 pi, right? So it is aromatic. Perfect. Similarly, 2, 4, 6, 8, 10. This is also aromatic, following the Huckel's rule. If you look at this one, 2, 4, 6. 6 pi electrons, aromatic. 2, 4, 6, 8, 10. Right? 10 pi electrons. So this is also aromatic. Right? 2, 4, and this particular lone pair, 6. 6 pi electrons. So this is also aromatic. Right? Now, among these two lone pairs, there is one lone pair that's in conjugation. So 2, 4, 6. 6 pi electrons, following Huckel's rule. So aromatic. So all here are aromatic, right? All here are aromatic. Now check these. Among these two lone pairs, one lone pair is in conjugation. So 2, 4, 6. 6 pi electrons means aromatic, right? 2, 4, 6, 8, 10. 10 pi electrons. 10 pi electrons, guys. What do you think? 10 pi electrons. Is it aromatic or anti-aromatic? Is it following the Huckel's rule? 2, 4, 6, 8, 10. This is also aromatic. Right? Similarly, look at this particular carbon. It's sp3 hybridized. So it's sp3 means non-planar. Non-planar means non-aromatic. Right? Similarly, this is also sp3 hybridized. So non-planar means non-aromatic. This sp3 hybridized. Non-planar, non-aromatic. Right? 2 plus 1, only 3 pi electrons. So non-aromatic. Right? 2 pi electrons, aromatic. 2 to 4 pi electrons, anti-aromatic. Right? 2 pi electrons, aromatic. So that's how you exactly check it. Yeah? Am I clear? Am I clear with all these guys? I hope all this stuff is clear. Well, I believe you can easily solve these sort of questions now. Say, 2, 4. 4 pi electrons means anti-aromatic. 2, 4, 6. 6 pi electrons means aromatic. This carbon is sp3 hybridized, so non-aromatic. 2, 4. 4 pi electrons means anti-aromatic, right? sp3, non-aromatic. Perfect. 2, 4, 6, aromatic. Right? 2, 4, 6, aromatic. All clear? Tell me the answer of this particular question. Or, this is the last question of the session, and I would want its answer in the comment section. It's a homework question. Right? This is the homework question. I would want its answer in the comment section of this particular video. And I would want answers from everyone. Perfect. In the last session, also in the thermodynamics session, I gave you one homework question. All the students did not try that homework question, I believe. Right? So if I'm giving some question, that means, right, you're supposed to write its answer. So I would be wanting its answer in the comment section of this particular video. Right? And everyone has to answer it. Be it right or wrong, does not matter. If it is wrong, I'll correct it in the comment section. If it's right, it'll be a thumbs up. Okay? Chalo, with this, I'll be taking a leave. And this particular PDF of this particular session, I'll be sharing in the Telegram, which is Wassim Bhat Chemistry Official. Okay? Chalo, I'm taking a leave with this. I'll see you guys in the next session. Till then.